Hello, everybody. Welcome. This presentation is going to be on faster, easier, simpler vectors, how to design software and programming languages. This right here is the most important slide of the presentation. Okay? Who thinks they know what this slide is about? Any, feel free to raise your hand. Anybody? Any ideas? Yes? Allocation performance as you push back. Great. Yes, that is maybe. Anyone else? Okay. Well, the important thing about this slide is it doesn't necessarily mean anything. There's no units, but it's the most important slide on here. And in fact, it means a lot of things. It means, yes, the performance as you push back on a vector. It's anything that has quadratic growth. But more important than just runtime performance, this is developer cost. It is source code growth rate at most organizations. It's super linear growth. And typically, it's a bad thing. But yeah, so keep this slide in mind throughout the presentation. This is what we're trying to avoid. So in this presentation, I'll be going over some ideals of software design, ideals of code itself, and then kind of narrowing that down into the specific. What types of vectors are there out there? We're all familiar with just the standard vector, the one in the standard library, but it turns out there's actually a lot of data structures that are really similar to vector. Some of them have the exact same guarantees but a different implementation. Some of them change the guarantees slightly to have slightly different performance characteristics to be better for certain workloads. And then we want to look at how to make it easy to write them. Because it doesn't help us if there's a whole bunch of different types of vectors and nobody can write any of them. Because then the only one we can use are the ones that other people wrote for us. It doesn't help if writing them costs a lot, because then we get that super linear growth. And then from here, we'll go into how to write software in general. What lessons can we learn from all these different types of vectors, all these different types of algorithms on vectors to do a better job of writing our code? And then from there, how to design programming languages. What can we take to empower our users to let them do the things that they need to do to write efficient, understandable, maintainable software? So who am I? I'm David Stone. I am on the C++ standardization committee, where I chair the module study group, and I'm the vice chair of the evolution working group. That is the group where we design new language features. And I also, my work experience, I've worked in finance for, maybe 7 years total, across a few different companies. I'm at QuantLab right now, working on high-frequency trading systems, where throughput is really important and latency is really important. But I've also worked on large-scale distributed systems and on autonomous vehicles. So again, systems where performance is at a premium, where you need to make guarantees of, things will run this good. So that's kind of the perspective I'm coming from. Performance matters. Some background, mostly just wanted to get some links in here. So Functions Want to Be Free is a presentation that I gave a few years ago, where I look in detail into the implementation of a lot of different algorithms. Notes on Programming is a paper by Alexander Stepanov you can read online. This, I think, is a really good summary of software design principles, specifically generic programming principles, the basis of the C++ standard library. And that is kind of the perspective that I'll be approaching this from, of wanting to make generic programming, separating data structures and algorithms, allowing you to combine them independently in an efficient way. That third link is a link to all of the source code that we're going to be going through today. It's a complete implementation of various containers, various algorithms. It's mostly following the approach of the C++ standard library, but with some updates, some changes to the interfaces. And then this last one is a really good presentation that I think touches on some of the things I talk about here on simple optimizations. I highly recommend it. It looks into kind of, how how optimizations work, how the compiler sees your code, and that simple optimizations are actually a lot more complicated than they seem. So, my approach for designing software is start at the goal. Think of where do we want to end up? What do we want our end result to be? And focus on efficiency and ease of use. Importantly, there are more interfaces than people realize. An interface is more than just a function signature. An interface is, what is the behavior? What are your preconditions? What is the time complexity? So I want to go a little specific, kind of ground this in reality a bit. There are a few different types of arrays that I want to talk about in this presentation. There's just array. That's the one we all know and love. And then there's uninitialized array. I go into detail in that in my presentation yesterday on static vector. So once the videos are up, you can watch it there. But it's basically an array that owns the memory, but not the objects themselves. It provides storage for objects. Uninitialized dynamic array, the same sort of idea, but now instead of the size being known at compile time, it is a runtime size. This is important because it makes implementing other containers much easier. And then dynamic array is similar to vector, but rather than having a capacity and a size, it has just a size. That allows you to have, you don't have to store that capacity, so your stack space is a little smaller. And then there's many vectors. There's a whole lot more vectors than people realize, a whole lot more than I realized before I started working on this presentation. There's standard vector. That's the one we all know. Okay. But then there's a 32-bit vector. So on most 64-bit systems, the data representation of a vector is a pointer to the data, a pointer to the end of the data, and either a pointer to the end of the capacity or a 64-bit size for the capacity. That takes up 24 bytes of stack space. A 32-bit vector would have a pointer to the data, a 32-bit size, and a 32-bit capacity. So that takes up only 16 bytes of stack space. Sometimes that matters. That makes operations like moves faster. It makes certain things optimize a little better because we know that the size is within a certain range. Static vector is just like vector, except the elements are stored within the object. There is no dynamic allocation. So if you allocate the static vector on the stack, your elements will be on the stack. This was my whole presentation yesterday. I'm not going to go into too much detail on here, but just kind of give the brief overview. Then there's a small buffer optimized vector. This is kind of, you can think of it as a variant of a vector and a static vector, except it has certain optimizations to where it's a smaller object and accessing it is more efficient. Essentially, when the vector has capacity for just a few elements, they're stored within the object. But if it needs to grow larger, it allocates memory instead. Then there's stable vector. This one is really interesting. It only works on certain systems. But if those are the systems you're deploying for, maybe the benefits it gives you are worth it. And what it does, what's interesting about it, is that it has a certain capacity, but it is it's basically a vector that always allocates a very large capacity. Think 4 gigabytes or larger. And it takes advantage of virtual memory so that the objects in the vector always remain at a fixed address. And as long as you don't actually use up that extra memory, if you have a 64-bit system, you have a virtual address space of, on most systems, something like 54 bits worth of address space. Even if your system only has, say, 8 gigabytes of memory. And that's fine. You need an over-allocating OS or some sort of virtual memory manager that allows you to do this. Or you can have a smaller stack footprint vector. So you can have a vector where you store the size and the capacity in the allocation, so the stack space of the vector is just a pointer. This is usually a losing performance trade-off because then you have to go to indirect memory to get to the size. But, and that's a cost on every begin, or rather on every end of the vector. So iteration is slightly slower. But the benefit is, say you have some sort of parser where you need to be able to store an int or a double or a float or an array of objects. If you were just use a regular vector, the size of each element in there would have to be 32 bytes, 24 for the largest element and then the discriminator. Whereas if you have a vector that has a smaller stack footprint, The data takes up 8 bytes, and the discriminator makes it only 16 total. So you've cut your size in half. And that could be a big win if you rarely have lists in the storage. So like a lot of these things are kind of niche, or they're used in this one specific area, and they're not for general use. But that's still important. Sometimes that specific use you have is a very important use to you. So now I want to show you what I believe to be a minimal and complete interface for vector. And now what I mean by complete is that you can implement every algorithm that you want to implement efficiently. And that's important. So there's the default constructor. Sure, that's exciting. There's a range constructor, the ability to construct from a range. In vector, this is done with an iterator pair. But I actually argue that the better interface is that it would accept a range, not an iterator pair. The iterator pair interface is kind of how it was designed originally, but I think we've learned a lot since then. Yes, Dave?
You have the range constructor, you don't need the default constructor.
So the comment was, if you have the range constructor, you do not need the default constructor. Yeah, so then you could basically construct from an empty range. That would be the effect of the default constructor. Yeah, it's purely a syntactic addition, I guess. So that is a very good point, and I'll get to that in just a second. Yes?
Since you're taking questions now.
Yes.
Do you have, so you said that the single pointer vector is not usually a win.
Yes.
Do you have experimental evidence for that?
Yes, the question was, do I have experimental evidence that the single pointer vector is not usually a win? Yes, it optimizes worse in some cases. I don't think I have the, I don't think I have that on my slides though. Yeah. Yes, yeah, we can talk some more after this, and I can try to find the data. Okay, then there's copy assignment and move assignment. Sure. The destructor, of course. And then begin and either end or size. You can compute size by doing end minus begin. You can compute end by doing begin plus size. Either one of those is necessary for a minimal interface. And in practice, it turns out that all existing, or all popular vector implementations store a pointer to the end, so that in effect, size is implemented in terms of end minus begin. But this generates worse code than a pointer and a size. This is for a few reasons, but one of them is that for optimizers, they do much better knowing the size that allows them to compute a trip count for loops. Certain operations just do better loading the size because you can do slightly different instructions there, but we're kind of stuck with this for ABI reasons in existing implementations. Then there's capacity, okay. And then append from capacity. This is a new one. There was a proposal to add this to standard vector that's been kind of delayed. We added something else to standard string for 23 that's still kind of getting discussed. But what append from capacity does is it allows interoperation between vector and, say, some sort of C function that requires a pointer. It allows you to say, hey, this vector has a pointer to data and it has spare capacity at the end. It would be really nice if I could construct stuff in that spare capacity and then tell the vector, hey, it is now this much larger. Now, this isn't a safe interface. This is a low-level interface that you're supposed to layer higher level algorithms on top of. But it turns out that without this function, a lot of really interesting optimizations are not possible. For instance, it is not possible to implement an efficient append on vector. You can call pushback in a loop, doesn't optimize as well as it could. You can call insert at an end, doesn't optimize as well as it could, and it has more requirements on the source elements, because insert at end could be insert at begin as far as the type signature is concerned, so you theoretically have to be able to shift elements over. Reserve allows you to add new space to the vector. And then operator square bracket. Now, there's an asterisk there, because operator square bracket is technically not required, except C++ says it's required. You cannot implement operator square bracket outside of the class. So if you want to have this operation, you have to have it in the class, so it's something you have to write. So this is it. With these functions here, you can implement every other algorithm you need on vector. You can implement pushback. You can implement erase. You can implement insert, sort. All of these functions that we have, some of them member functions, some of them free algorithms, we can do efficiently with this basis. Now I want to talk about initializer list. C++11 added initializer list, which is a way to easily create a list of elements and add them to a container. A really nice interface. The problem is that initializer list is actually a reference type. It's a reference to a constant array. This means a few things. Specifically, it means that you cannot move from the elements. That's kind of sad. That's a really disappointing performance loss. If you create an initializer list of strings, you're going to copy from those strings every time. That's sad. There's another issue with initializer list, which is sometimes called constructor hijacking, or the not so uniform initialization syntax. And that's that if you use the curly braces, and it could be interpreted as an initializer list constructor, it will be. And this is bad for generic code, because when you're writing generic code, if you want to construct a vector and you use curly braces, and you say, you put some arguments in there, sometimes it'll be an initializer list constructor, sometimes it might be the size and value constructor, and that depends on the type of the vector that you happen to be using, which type of constructor you use. That's unfortunate. But we can do better using C arrays, our good old friend. When you accept a C array using a syntax like this, and C array here is just a type def for a C array, just an alias template. So that way, this syntax is much easier to read than a reference to array syntax. That's all that's going on here is a type def, nothing tricky for the top one. So this accepts an R value reference to a C array. And what that means is you think about the constructor a little different. With an initializer list constructor, when you use like vector, open curly brace, arguments, close curly brace, you're saying, I'm constructing a vector from this list of things. Except what you're really saying is, I'm constructing a vector from this thing, this thing, this thing, this thing, this thing, and this thing. And this makes the syntax more explicit that I'm saying I'm constructing this vector from a list of things. Because what you would say is vector, open paren, and then the one thing I'm constructing is a list of things, so open curly brace, list of things, close curly brace, and then close paren. So you have a single argument constructor, and that single argument is a C array. And then it's explicit which type of constructor you're trying to call. But now C arrays have a problem as well. You cannot have a C array of 0 elements. So if you used empty curly braces, that would fail. So that's what this second constructor is for. There's just an empty type named empty C array parameter, whatever. The name doesn't really matter. The point is just an empty type that's default constructible, so it can be constructed from empty braces. So now you might be thinking, okay, what's up with this like standard same as template parameter nonsense? Like, why doesn't it just accept the empty C array as a parameter? And the answer is ambiguity. If it accepted the empty C array parameter as just a regular function parameter, then when you said vector, open paren, open curly brace, close paren, do you mean to default construct a vector and move it in, or do you mean the empty C array parameter? So this resolves the ambiguity to make sure that the syntax always works. So now I want to talk about allocators. When you start saying, okay, there's all these different types of vectors and all these different performance characteristics you can get out of them, it's natural to think, okay, can allocators solve this problem? We already have this designed into the language. Can we press it into service here? So the value proposition for allocators essentially comes down to writing containers is complicated. Sometimes all that users want to customize is how they allocate the memory. So let's just let them customize that one piece. Sounds reasonable. But there's some costs with allocators. There's a size overhead. For instance, if you try to implement a static vector with a stack allocator, you have a pointer to the data, size, a capacity. The allocator has to have a pointer to the memory resource, and then the memory resource has to have a stack offset. So there's all this size. Whereas with a static vector, you just have the size. And then there's also the performance overhead of using it. All accesses are indirect. when you use a vector with a stack allocator. Now it's indirect to stack memory, which is hot in cache, sure, but it's still accessed through a pointer. And none of your operations can be trivial. Whereas a static vector, everything's contiguous, everything is as trivial as it can be. That's nice. And then there's also the code overhead of using allocators. If you use a vector with a stack allocator, you need to construct the memory resource before constructing the container. And it turns your vector into a mixed value type reference type, which means that regular value semantics are trickier. You have to be careful to make sure that the memory resource outlives the container. Static vector, just use it. So I want to go back to this value proposition for allocators. It said writing containers is complicated. Let's let users just customize this one thing and make that one thing simple. I think there's another solution, separate from allocators, which is make containers simple. Part of what's complicated about containers is that you have a whole bunch of member functions, a whole bunch of type defs, a whole bunch of things that can be determined from other things. And you have to remember this long sort of incantation of, oh, I need to have a begin, an end, a pushback, a popback, an erase, an insert, and I have to get insert right, and insert's really hard to get right. So let's look at some principles of software design. Reusability. Reusability is great. We love software reusability. I would define reusability as saying, if you encounter the same problem again, you can take the code that you wrote and you can use it to solve that problem here. And that's pretty good. But sitting above reusability, I would say there's composability and genericity. Composability is saying, I can take these other things that I've used to solve problems, I can combine them together to solve a bigger problem. And genericity is saying, hey, I solved this problem for this one type before, and I can make that solution generic across multiple types. And when we combine all of those, we get simplicity. And that's our goal. We want efficient, simple, easy to understand code. So I want to go to some code examples here. Let's live demo. Let's see how well this works. Oops. Okay. So here is a vector implementation, kind of going by what I showed. As you can see, it's not very large. 145 lines, including white space, comments, closing braces, all of that. And part of that is a little misleading, just because a lot of the complexity of vector is in algorithms that aren't here. So let's look at some algorithms. Let's look at, say, pushback. Okay. Already we see something kind of interesting. Let me make it a little bigger so it's visible. Hey, pushback doesn't really look like there's doing much in there. So in C++, we have pushback and we have emplaceback. And pushback can be implemented in terms of emplaceback. But it turns out there's actually an even lower level or an even more powerful facility, and that would be a lazy pushback. There's a proposal for C++ to add lazy function parameters, and it's one of my favorite proposals. And effectively what it does is it just takes your expression, wraps it in a function, and then you can call the function inside your implementation. And so why is that so good? Why is that so powerful? What does it do that emplaceback doesn't do? Now, with emplaceback, you pass a list of arguments, and those are used to construct your value inside the container. That's nice. But there are some things it can't do. It cannot handle guaranteed copy elision, for instance. So if you have a function that returns a value, and you pass the result of that to emplaceback, you'll construct the value, pass it to emplaceback, and then emplaceback still has to do a move. That's kind of sad. We would like to be able to avoid that move entirely when possible. That was kind of the goal of emplaceback, was to avoid unnecessary moves. But sometimes that operation has already been decomposed into a function. Sometimes it's not just a list of arguments. Sometimes it's more than that. So let's look at what lazy pushback looks like. So basically the lazy pushback here is just, let's see, is that the right size? Yeah, that's reasonable. Is trying to do a manual implementation of lazy parameters where the user has to explicitly wrap their code in a lambda. But then we can provide things like pushback on top of that so that users don't have to worry about that if they don't care. So how do we implement lazy pushback? Well, there is some sort of way for containers to opt in saying, you know, my container is special because it doesn't follow some sort of generic thing. Sure, can do a member. An example of a type that might use this would be a linked list. The remaining implementation is kind of vector specific, so a list isn't really going to follow that. So then we go to the else branch. That's the real meat of this algorithm. This is the more generic thing. And the goal here with the generic programming is that you want to find a way to decide, like, you know, what are the fundamental operations that this requires, and implement it in terms of that. In terms of, like, what concept are we requiring out of this? So when we look here, we need to, let me back up a little bit. One of the interesting requirements of pushback that a lot of people don't realize is when there's a reallocation, you need to make sure that everything works properly. That's the easy part. The hard part is that you can push back elements of a vector into a vector. So you can say, you know, vector pushback vector at 0, and that needs to work whether there's a reallocation or not. But you can do that efficiently, and that's what we see here. So kind of walking through the code, we see if the initial size of the container is less than the capacity, that means we don't need to reallocate. We first construct the new element, and then we append from capacity. Cool. And then otherwise, if the container is reservable, so for instance, vector is reservable, you can call reserve on a vector, then we default construct a new container because we know, yes, Dave.
Sorry, isn't the final size be less than the capacity that should get you into this branch? How is the addition size?
The question was about the comparison that I do of size versus capacity. So if the size is currently less than the capacity before we add the new element, that means...
It's always less than the capacity. That's an invariant, right?
No. Let's say you have a container with a capacity of 4. It can hold 4 elements before needing to reserve. So the size will be 4. The capacity is 4. Yes. So when the size is less than the capacity, we know that there is more capacity that we can use. Yes, no problem. Okay, so then we say, okay, now if we can call reserve on this container, then we need to reserve new space. So how do we do that using just the operations we've already seen? Well, we can do that by creating a new container. It's empty, default construct it, and then reserve the space we need. Now, reserve the space we need is actually kind of a hard problem. How much space do we want to reserve? We don't want to reserve exactly what we want, because then we would get that horrible quadratic behavior that we saw before on the graph. Because you call pushback, reallocate memory, copy everything in the vector. Call pushback, reallocate everything, copy in the vector. That'd be bad. So instead we want to reserve extra space. We want to have some sort of exponential growth, and that's what this reallocation size does. This is the kind of the one location that we can control all reallocation that we need. So most vector implementations double on every reallocation. Other vectors use other growth constants, but you know that can all be handled here. It's not important as long as it's multiplying by a constant, so you have exponential growth. So we reserve all of the space we need, saying, you know, this is our current capacity, this is how many elements we have, and this is how many we're adding. So that way it can figure out exactly how much it needs to reserve. And then we construct that new element into that new container. And we do that first because we're about to move from all of the other elements. And so we construct the new element first, so that way, if it's a reference to an element in the vector, we're fine. So we construct the new element, and then we do uninitialized relocate, no overlap. So this is, I talked about this a bit yesterday in my presentation. What uninitialized relocate, no overlap does is kind of similar to uninitialized move, but with some optimizations applied. It says, first of all, the no overlap. That's straightforward. That the source and the destination have no overlap between them. That enables certain optimizations. For instance, for trivially copyable types, we can use memcopy. That's great. We want to be able to use memcopy whenever we can because memcopy is fast. The next question is, what does this uninitialized part mean? That just means that the destination range does not have any objects alive in it. We don't do assignment, we're doing construction. And then the final kind of thing of what's going on here is the word relocate. What is relocate versus move? A move takes an object and uses it to construct another object and leaves the source in some unspecified state. But there is still an object there. A relocate is a combination of a move and a destroy. This gives us two benefits. One benefit is that if we did an uninitialized move, then what we would need to do after that is go through the source vector and destroy each element in turn, which means we have to visit each element twice. That's more work than we have to do. By bundling it up into a single operation, we do the move and we do the destroy right away, so we only have to visit each element once. This is, good from just a sort of an obvious, it's good to iterate over things one time perspective, but it's also good from an optimization perspective, because the optimizer is able to see, I did a move, I did a destroy, no intervening code that I have to track side effects for. That's important because when you consider something like unique pointer, when you do a move from a unique pointer, it sets the pointer to null, and then it calls delete on the destructor, or in the destructor, I should say. Now, by putting that code closer together, it makes it more likely the optimizer will see, oh, I set the pointer to null, and then I call delete, and delete checks if the pointer is null. So it might be able to just elide both of those calls. That's nice. But then there's a further optimization that we can do here, which is, for instance, this optimization is found in Facebook's Folly library. Clang has attributes that you can use to try to add this to your own types, which is the concept of trivial relocatability, which is that many types, most types in fact, for instance, vector, unique pointer, most containers, are trivially relocatable, meaning that if you have a source object and you have a destination object, and you just memcopy the representation of one onto the other, that's enough. That is a relocation. You can skip calling the destructor. You've done everything you need to do. So the uninitialized relocate, no overlap algorithm bundles all of that up together. Yes, question? Okay, so the question was about basically how that relocation works. So when you do the memcopy, if something is trivially relocatable, you do the memcopy and then you do not call the destructor on the source. Yes, correct, not on the elements, because you've memcopied the elements over. That is the trivial relocation. That is the combination of the move and the destroy. So for instance, consider unique pointer as a simple example. It just has a pointer to data. If you memcopy that pointer, so you just copy the pointer value, the new unique pointer points to that data and owns it. And the old unique pointer, it just has some bytes. You don't want to call the destructor, because if you called the destructor, you would interpret those bytes as a pointer and delete the data that you now own in the other unique pointer. So the trivial relocation kind of allows you to skip calling the move constructor followed by the destructor, because you're saying a memcopy has the same effect.
Sorry, I have to interrupt. Just for the benefit of our online audience, if we're going to have a conversation, the questions need to come up to the microphone.
Okay. But yeah, so to summarize what he said, and then further questions can make sure they come up to the microphone. It was that for types that are not trivially relocatable, what happens? And for that, it would be a relocate operation that does a move constructor immediately followed by destroy the source. So it builds up the operation from those two pieces in the case where there isn't a more efficient way to do it.
We have a question from online.
Okay.
Isn't trivially relocatable the same as trivially copyable and trivially destructible?
Okay. Not quite. So for instance, unique pointer is a great example. Unique pointer is trivially relocatable because basically in general, types that are trivially relocatable are those that do not contain any sort of pointers back into themselves. So unique pointer is trivially relocatable despite not being trivially destructible. You have to call delete, and not even being copyable at all. It is relocatable though, trivially relocatable, because you can copy the pointer and skip calling the destructor, and now it's as though you've moved the unique pointer there. For all of the details on this, I would recommend watching Arthur O'Dwyer's talk on trivial relocatability or reading his blog post. You can just search Arthur O'Dwyer trivial relocatability, and it'll pull up good stuff there. And that'll go into all of the details you need to know, and probably some that you don't need to know. Okay, so back to pushback. So here we constructed the new element, we moved all the old elements, and then we need to say, okay, now our new vector has the capacity, or rather the old vector doesn't have anything in its capacity anymore, so set the size to 0, essentially, negate the original size. And then the new vector has the initial size plus 1. And then move assign does everything we need. That handles the reallocation case. And then in the case where it's not reservable, for instance, static vector, we say, okay, you've run out of space, you're trying to add space, you can't do that, that's unreachable code, that's undefined behavior. Another approach that you could take here would be throw an exception. That's another thing someone could do for static vector. And the interesting thing about this approach of fully separating the data structures from the algorithms is that with regular vector, if you don't like pushback, too bad. That's the only pushback you have. You can't implement pushback, not in terms of pushback, with vector. Whereas when you make sure that you have kind of these lowest level basis operations that are as efficient as possible, it would be perfectly reasonable to pull out this relocation, or this reallocation code into a pushback with reallocation function that assumes reallocation is necessary. And then it's really easy for for your user to say, oh, I need a pushback that throws for things like static vector. And they can just build that up with just a few statements. And yes, there's a question.
Since your vector API does not seem to rely on C++ allocators, do you also do optimizations based on realloc?
Okay, so the question was about realloc. No, I don't do any optimizations based on realloc, and there's a reason for that. That was actually intentional. In C++ 23, there is a new allocation function that when you do an allocation, it returns back to you the size of the actual allocation that it did. You can read the paper on that for the proposal, but the reason that the C++ committee went with that API is that realloc it has a lot of problems, I guess. It's not always possible to do. I don't have enough time to go into all the details of the issues with realloc, but the point is that once that C++ 23 feature is implemented, where there's a more efficient allocation API, I can say, okay, allocate 20 bytes, and it'll say, oh, hey, the memory allocator actually just rounds every allocation below up to 32 bytes. So you actually allocated 32 bytes, and then the vector says, oh, okay, cool, I have 32 bytes now. And that kind of negates a lot of the need for realloc because you already know you're in the largest amount of space that you have. So realloc wouldn't do anything useful. Okay. So let's see. So we talked about pushback. Let's look at one more function here. Let's look at append. Append is really interesting. So with append, our goal here is we have a container, we want to add a bunch of stuff to the end of the container. How do we do that efficiently? Now I made the claim earlier that it is not possible to efficiently append to a vector. So I want to try to back up that claim a little bit. So actually, rather than looking at code, let me pull up Compiler Explorer. Let's look at some assembly output. So let's make that a little bigger. I don't think you can read that. Is that legible? Can people read that? Sure. Okay. So in the leftmost pane, we have some source code. The middle pane is the assembly output for standard vector. And the right pane is the assembly output for the vector that I wrote. This is running with the latest version of Clang with O3, no debug asserts or anything like that. So trying to make it as fast as possible, as good of code as we can get. And so this first code that we're looking at is pushback in a loop. So we construct a vector, we reserve enough space, and then we say, n 0 to 4, call pushback. And then we look at what happens. We have this assembly output here for the middle one. Let's see if I can try to, that's probably too small. Okay, so on the right, let's start there. That's a bit simpler assembly. It does exactly what we would expect it to do, which is we call operator new, that's our reserve. And so everything after that is the pushback. So we add zeros into each position that we need and don't really do very much else, okay? Whereas in the standard case, we add the zeros everywhere we need, but then there's also extra stuff. For instance, this LEA instruction is load effective address. That is a multiply add combination instruction. And the reason for that is the data representation of standard vector using a pointer for the end instead of a size. It has to do slightly more complicated arithmetic to advance it each time. And the pushback isn't quite as good as it could be. Now, it's not super important to read all of the assembly on here. I've also run benchmarks on it, and the assembly differences are measurable, like maybe 1 or 2% overhead. So not a lot, but still measurable. And for some domains, that's enough measurable. The important thing here is kind of keep track of approximately where this is, and we'll compare this versus different code to see what the assembly ends up changing to, I think is a kind of a helpful way to look at it. So we looked at pushback. Let's look at insert at the end.
We have a question from
Yes.
online, just going back to pushback, the implementation.
Okay.
Specifically lines 61 through 63. You can find those.
Okay.
This is in the case when the stack vector can't be grown further. That's the context of the question.
Yes.
Is stack vector limited by its C++ implementation, or is it due to the stack memory not being valid or in scope anymore?
Yeah, so static vector has a compile time capacity. When you create the type, you give it a type template parameter and a capacity template parameter. So when you say, okay, the capacity is 10, that means you have stack space for exactly 10 elements and no more. So just built into the type and built into kind of how stack memory works, it is not possible to grow that because there theoretically could be data after it on the stack at that point. And in fact, static vector isn't the only vector type where you have this behavior. For instance, I talked about stable vector earlier on that relies on an over-allocating OS and virtual memory. The stable vector also never reallocates memory. It allocates memory on construction and never reallocates again. So if you were to hit the limit there, that also means, okay, you've exhausted the memory that you said this was going to take up. That's another case like that. There are multiple types of vectors where you cannot reallocate anymore. Okay, so back to the assembly listing. Another option, we could try to insert at the end. And we see the standard vector code is even worse than with the pushback in a loop. We see here it added in some exception handling code to be able to sort of roll back and delete any memory, even though we know that the only thing that can throw an exception is this call to reserve, and then there's nothing to roll back at that point. Is basically just there was too much stuff for the optimizer to see through. And then if we look at, append, So again, just trying to use insert, not all that exciting. And then over here on the right, we have, I think, the ideal insert, or at least as good as I could convince compilers to generate. See, it's fewer lines of assembly than anything else. There are no branches here other than in the call to operator new to allocate the memory to begin with. But importantly, it just creates some data and copies it in with some instructions, about as simple as you can get, even better than the pushback case. And that's what's important here. If I'm trying to write append and all I have to work with are insert and pushback, I get worse assembly than if I can write append directly. And the reason is that I can use append from capacity in the implementation of append to just construct the elements where they need to be and then tell the vector, by the way, your size is now here. So that's what I mean when I say that it's important to write sort of efficient operations for your type. So, does your code look like this? Do you write your types thinking in terms of what is our efficient basis operation? What is our data representation? And what are the algorithms that operate on the concepts that that data representation applies to? So I'm going to go back to how I write code. Start with the use case. All of this of me writing containers began because vector wasn't fast enough for me. Vector specifically wasn't fast enough for me for the use case that I had. For some use cases, it's perfectly good. So instead, I wrote static vector. And I needed a size optimization, and I needed to store everything in there, and that was good. And then I had another use case where vector wasn't fast enough, but I still needed dynamic size. And I knew the software was always going to run on an OS that had over-allocation of memory. And that's why I wrote stable vector. And then once I have all of these vectors, I think, it'd be really nice if it were easier to write these things, if I could write all of these kind of individual algorithms to the concept of a vector-like type, a container with contiguous memory. That's kind of the fundamental thing that I'm trying to get at. I have data laid out in memory. How can I operate on that data efficiently? Then look for similar problems. Think, okay, where else can these solutions be applied? How much change do they need? What are the things that I need to do to extend this to another problem? Because once you have the solution and you realize kind of this change in your thinking of, it's okay for me to write a vector if it is better for my use case, then you start seeing there are a lot of use cases that are performance sensitive where the standard vector is pretty good, but we could do better, and we're already spending time optimizing there. And I try to find what is a direct expression of the solution to this exact problem. We've survived for a long time without append. We do pushback in a loop. We call insert at the end. We do these things, but the conceptual thing we're trying to do is append to a container. And once you think that, it says, okay, I'm trying to append to a container. Why am I calling a function called insert? I'm not trying to insert. I'm trying to append. So then you write append, and then you realize, wait a second. Writing this append isn't as efficient as it could be. It's requiring more of the types, or it's not optimizing the way you want to. And it's important that your solution does one thing. Don't solve a problem you don't have. I'm not advocating just go out looking for problems and be like, I've got the solution. It's a pretty nice solution. I bet I can use it everywhere. Try to make sure you're actually solving real problems, obviously. And then figure out how does it generalize. What abstraction am I trying to provide to people?
Oh, David.
Oh, yes.
Question. Is there any accepted test suite to validate a custom container or even just a vector implementation? And is there any accepted or well-used optimization benchmark to compare these implementations?
Excellent question. So one of the benefits of making sure you completely separate your algorithms from your data structures allows you to test only the things you need to test. When I write a new vector, when the interface is just that minimal interface I showed of just a few constructors like special member functions, begin size, and capacity, and reserve, that's a whole lot less that I have to test. I don't have to test the behavior of insert on this container because I already have tested the behavior of insert on things that conform to this interface. So when I'm doing my testing, I test reserve, I test append from capacity, and these are all much simpler things to test. As far as benchmarking goes, I don't know of any really great solutions. The approach that I took was I started out just kind of writing the code in like following good principles of efficient optimizable code and didn't worry too much about the benchmarks at first. Then I took the code and I put it into Compiler Explorer and made sure that my output was reasonably good. Like I wanted it to look pretty much like what the standard vector looked like because I knew that was at least reasonably well optimized, probably really well optimized. And that showed a whole bunch of examples where I had some code where it wasn't actually doing enough. And I looked at, okay, why, like go through, keep pulling pieces out of the code until I get down to just the bare essentials of what is this higher level algorithm trying to do, pull out all the abstraction in between it until I see, oh, when I remove this check, the code optimizes better, and I didn't need that check. So what can I do to optimize that a little better? And then the final step that I did was I took the benchmarks that libc++ has for vector, and I ran them against my own code. And that actually had a really interesting effect. There is an article by Dan Liu about, I think it's 99th percentile latency. And in it, he talks about how the things that you measure are the things that you optimize. And the things that you don't measure are as bad as they can be while still meeting the requirements of the things that you do measure. And that's what I ran into here. When I ran some of the existing benchmarks that libc++ wrote, I found that my vector was about the same for like 0 and 1 elements because there's not really much to do there. But for small amounts of elements of maybe 1,000, 10,000, 20,000 elements or less, somewhere in that range, I was able to beat standard vector by a little bit. Some of the benchmarks actually end up being as much as like a 5% difference. That's pretty good. But that was kind of the code generation that I was getting when I looked at Compiler Explorer because most of the stuff I did in there dealt with fairly small amounts of data. But the compiler is really smart. It has a lot of optimizations. And those optimizations change based on the expected amount of data you have. And library implementations change based on the amount of data you have. So in the benchmark, when I got to large amounts of code, large amounts of data rather, vectors of 1 million elements, I hadn't looked at that. And then I was 30% worse than the standard vector. So it's, it was a real eye-opener, a real lesson of just how important it is to have lots of different ways of doing it. And kind of the reason that I started with Compiler Explorer was just, it's a faster turnaround time. I can make a code change and I can immediately see, did this change the assembly at all? If the answer is no, I don't have to benchmark. If the answer is yes, then sometimes it's like, oh, it just deleted a branch that didn't need to be there. That's almost certainly going to be a win. And then a lot of times it's like, okay, it's different. And then I benchmark. So, does your programming language help you? One of the downsides of the approach that I outlined is that when you do this separation, you end up with a lot of free functions, which means that you have kind of this inside-out logic where you're saying, okay, do this thing to the result of this thing to the result of this thing to my vector. Whereas when you had member functions, you would say like vector.pushback instead of pushback vector 5. And that's kind of sad because we read left to right, but to understand code with lots of free functions, sometimes you have to read it inside out. Now there is a proposal that I really like called a pipeline rewrite operator for C++. Hopefully it'll make it into C++ 23. I don't know. It needs a new update. But basically, it takes the idea of, you might be familiar with pipeline rewrite operators or pizza operators from other languages, where it's a pipe and what is that, a greater than symbol? I guess for you it looks like that. And that allows you to take these free functions and chain them in the right direction, to where you start reading left to right again without requiring this sort of combinatorial explosion. Because the problem with member functions, and the reason that most algorithms in the standard library are free functions, is kind of the ideal of generic programming, to separate out the representation of the data from the operations on the data. You don't want to have to make every single person who writes a data structure also implement sort, for instance. That would be sad. You don't want every single person who writes a data structure to have to implement binary search or set symmetric difference or rotate or any of these algorithms. You want to be able to just write the algorithm once and write the data structure once. That allows you to have linear growth instead of quadratic growth in terms of the source code as you add algorithms and as you add data structures. Things wrong with my code? Yeah, that's it's always a hard thing to talk about, I guess. But yeah, so I mentioned one, this sort of right to left thing. There's also like, I would say that that's kind of the major issue. And then kind of going back to, does your programming language help? There's sort of the package management thing. There's, can you even change to a new data structure if you have binary compatibility issues? Things like that. But another thing is that there are some things that we cannot do in C++ because our programming language doesn't help us. For instance, the range constructor for every single container looks exactly the same. It takes the range and it calls the algorithm assigned to empty. Every single one does the same, but you cannot implement a constructor generically. It has to be per type. The copy constructor for every type is exactly the same. It's just a range constructor, but copy constructors can't be templates. Therefore, it has to be implemented on its own. I have to have two constructors for C arrays because C arrays can't be zero size because we don't like zero for some reason. And there's a whole lot of these little sort of niggling details. We can't have a free function operator bracket. That's disappointing. Lots of things like that. Some constructors are boring. Copy assignment, always boring. Copy assignment is the same thing for every algorithm, but the assignment operator must be implemented as a member. Braced initialization should be boring. That's sad. But we talked about that a bit with C arrays and initializer lists. Begin duplicates code. The const and non-const overloads of begin are the same for every container. We are getting something that I think will help a little bit in C++ 23, which is deducing this. Ben Dean has a talk this year, I think, on deducing this patterns. So if you're interested in that, I recommend going to his talk. Some moves are expensive. So this kind of comes down to the issue of relocation versus move. We don't have relocation support built into the language. So we do a move constructor, and then we do a call to a destructor, but that doesn't always generate the code that we want. Swap does not compose, meaning if you have a data structure, you need to write your own swap for it because the default swap won't actually optimize properly. But then if you hold that data structure in another container, that container needs to write its own swap because swap isn't going to pick up the swap of the data members. It's going to do the generic one, which doesn't optimize properly. Now, the solution to this, I think, is either relocation might be able to save us, or better optimization, but since no compiler optimizes this right, like it's a difficult problem. It's not just you can just fix it and then they fix it. Like it's a hard optimization problem. I think, yeah, that is all I have. I believe I am out of time. So I guess that's all the time I have. Thank you all.